Now let's do a little review of stubs that are open-circuited or short-circuited on the end. You've already seen this. This was section 2.7, where we can either have a length of line with a short circuit or a length of line with an open circuit on the end. If you review section 2.7, you'll remember we had two equations, one for the short-circuited case and the other for the open-circuited case, and they help us find the input impedance that's right here at the front of their line. You can see for the short-circuited case, that's a tangent equation, and for the open-circuited case, it's a cotangent equation. We can create inductors or capacitors from either one of these lines just by comparing it to the impedance that we would expect from an inductor or the impedance that we would expect from a capacitor. We can find equivalent capacitors by controlling the length of the line. Here's an inductor with the length of the line controlled, or a capacitor with the length of the line controlled. So there are equations for the equivalent inductance based on length or the equivalent capacitance based on length. Now let's see what that means in terms of a Smith chart. Let's suppose we had a short-circuited stub. That's just a short-circuited length of line which has an impedance of 0 at the end. So let's plot our load impedance. That's where the real part is 0 and the imaginary part is also 0. Right here is the location of our load, and that's the location of a short circuit. And then, suppose that I wanted an input impedance of 100 ohms, and that my transmission line is a 50 ohm transmission line. So let me plot my input impedance, and then what we're going to do is find the length of the line that will allow us to transform the input impedance we want to the load impedance that we have, or the load impedance we have to the input impedance that we want. So let's normalize Z in. That just means that we're going to multiply it by 50 ohms. So we're going to plot minus J2. The real part is 0, so it's all going to be on the outside of the Smith chart. So let's go down and find the Z in point, which is negative J2. That's right here. So this is the Z in that we want. The nice thing is that we can see we can go from our short circuit to the impedance that we want just by staying on the outside and rotating around the Smith chart. So which direction are we going to go? If we started our load, which is right here, if we started our load, we're going to rotate towards the generator to the desired input impedance. This is the toward the generator direction, and right out here we're at 0. We're going to rotate a length towards the generator until we get to our input impedance. So let's do that. Watch us rotate towards the input impedance that we want. Now how far are we going? We've just gone 0.25 wavelengths. Now we've gone 0.27, 0.28, 0.29, 0.31. Right here, if we draw a straight line from the center of the Smith chart out through the point that we're looking at, we've gone about 0.325 wavelengths towards the generator. This is the distance L. We have found the length of a stub that will allow our short-circuited load to become the input impedance that we want. The length of our stub is given right here. It's 0.325 wavelengths. Now what would have happened instead if we had had an open-circuited stub instead of a short-circuited stub? In that case, ZL would be infinity, and this would be the location of our open circuit. That would be the load. In that case, we would still want to find a length of line that gave us this input impedance, so we would just rotate across like this, same direction, and the distance now is going to be, the length now is going to be 0.325 minus the 0.25 wavelengths that we started with, so I need a stub that is about 0.1 wavelengths long. In fact, to be more exact, this is going to be 0.075 wavelengths long.